So we talked about connectivity-based clustering, and let's move on to centroid-based clustering. So although we already mentioned what centroid is, so this is the average point out of a cluster. Well, there is a clustering method that is driven by centroid. So kMeans algorithm is one representative example for that, and this is very widely used. So compared to hierarchical clustering, this is actually the foremost choice of a clustering algorithm. So here the motivation is the drawback of the hierarchical clustering that we discussed. So hierarchical clustering can cost quite expensive in terms of time and space. And well, for real life, we have data set often larger than 1,000, often larger than 10,000, or even more. So we need more efficient algorithm. So unsupervised algorithm again, and here kMeans. K is the number of clusters in clustering algorithm. So I want to find 5 clusters out of my data set. K becomes 5. I want to find 3 clusters. K is 3. And it is usually very smaller than the size of the data set. Let's talk about the pros and cons first. So kMeans algorithm, since the motivation is to come up with efficient algorithm, it is basically best compared to hierarchical clustering algorithm. But at the same time, it has other benefit. So it is very easy to understand, easy to implement, and easy to operate. So I implemented my own kMeans clustering algorithm when I was my senior year at Handong, and it already converges. So there is a criterion that is defined by, well, we are going to discuss this later on, but in essence, the training algorithm of kMeans, that is something called as EM algorithm. And behind the foundation of EM algorithm, there is Jensen's inequality. But at the same time, it has cons. So it is stopping at somewhere, but there could be local optimum. So, well, you have come up with some cluster result, but that is not correct and very far from what you want. So that is local optimum. And that is sensitive to initialization as well. So, well, soon you will understand what this means. And it is sensitive to outlier. So maybe your data set has some outlier. K-means algorithm by nature, if you have outlier, the result may be misleading. So here is the brief idea of kMeans algorithm. So you have set up n data points, and you start with k clusters. So initially, well, it is starting from some kind of random assignment of those clusters. And in order to conduct this clustering, you want to define one of the distance metric. So you want to measure the distance between cluster center and its individual data points. And the goal of this kMeans algorithm, we want to adjust the cluster membership. And we also want to adjust the cluster centers. In other words, these cluster centers means centroid. So we want to adjust these two. While we are doing that, we want to minimize within cluster deviation. So within a single cluster, we want to minimize the distance between each data point and cluster center. So what I just described is summarized in this simple notation. So we want to minimize the distance between individual data points. And MI over here, this is ith cluster center. So you want to measure the distance between individual data point and cluster center, and you want to minimize it. So you're taking the summation according to the cluster membership, and you want to go over all k different clusters. So if your choice of distance metric is Euclidean distance, well, you can rewrite the above notation in this form. So this is with Euclidean distance. So this is the idea. And this is the procedure. So where we want to sort of assemble the previous component into an algorithm. So you start by picking k, so that is the number of cluster, and you initialize the cluster centers. So you try to pick k different points in your data region or data domain. And if you pick those cluster center, based on the closedness, you can come up with the initial membership of the cluster. So the initial membership to the cluster for individual data points. So from now on, what we want to do is try to update the centroid. So like we discussed, we want to adjust two things, cluster membership and cluster centers. So number one and number two here, we're basically representing that. So each time you want to update the cluster membership according to the current location of the centroid. Then after you update the membership, out of the cluster member, you want to update the location of the centroid. So membership centroid. And if you do so again and again, to the cluster center, they will not move anymore. So that's what convergence means. So those cluster centers, they are converging to a specific point. That is when you want to stop. So like we discussed, well, this is number 3 is guaranteed. So your algorithm will converge in some point. So next coming few slides, these are animation, and you can just go through this animation and understand what is going on. So well, next time we will resume our discussion from here, but well, at the same time try to take a sneak peek of the next few slides. Then you can simply understand what this is doing.